Hi, my name is Dean Sacoransky. I'm a researcher at Queen's University in Kingston, Ontario, Canada. In this research, we present a single modality radar perception system for autonomous vehicle path planning. We suggest a modification of roadside infrastructure through the installation of reflective lane markers. We also present a clustering solution for segmenting radar point clouds into two classes, retro-reflectors and noise. We tested our approach via indoor experiments that make use of a Continental ARS 408 radar unit, a Husky A200 mobile robot, and a Vicon motion capture system for ground truth validation. We were able to successfully predict which radar returns correspond to roadside landmarks, thus enabling autonomous vehicle path planning and localization. This research is explained thoroughly in our paper titled "Towards Unsupervised Filtering of Millimeter Wave Radar Returns for Autonomous Vehicle Road Following." Current lane detection systems employ deep learning models trained on rich camera and LiDAR data for detection of key points and pixel-wise segmentation of lanes. However, these systems will fail in extreme weather conditions. Cameras, for example, are unable to perceive the environment under poor visibility conditions due to their operation in the visual spectrum. A similar problem exists for LiDAR, which operates in the infrared spectrum. This leads us to ask, how can we localize an autonomous vehicle in poor weather or lighting conditions, such as when the painted lane lines are not visible in the visual or infrared spectrum? We are developing an alternative solution which uses radar as the main exteroceptive sensor and reflective lane markers as localization landmarks. Radar has emerged as an essential component in the autonomous vehicle sensor suite due to its ability to perceive the environment in inclement weather conditions, its low cost, its advantage in direct measurement of relative velocity, and the fact that many modern vehicles are equipped with pre-installed automotive radar units. Retro-reflectors are devices used to reflect radar signals back to their source with enhanced detection stability. They are typically made from materials that have a high radar cross-section, which means they reflect radar signals back to their source with a high level of efficiency. We leverage these properties and use retro-reflectors as localization landmarks to help better define the path of the road. Perhaps the greatest challenge facing radar-based perception systems is the sparsity and noise of radar data, which can be seen clearly, for example, in this live visualization of 2D radar point clouds. The radar has poor spatial resolution and is susceptible to a high rate of false positive detections. Given these issues, we ask ourselves, how can we predict which radar returns correspond to a reflector point or a non-reflector point? That is, what we call a noise point. This is the question we aim to address in this research, and our solution lies in unsupervised learning, namely DBSCAN clustering. The raw radar data from the sensor is parsed to form feature vector F at time step I through a Ross melodic driver. This feature vector is comprised of the 2D Cartesian spatial coordinates and radar cross-section values of all inferred objects. We normalize the features using a standard scalar and use DBSCAN to classify each data point as either a noise point or a retro-reflector point. Here, we see the output of DBSCAN clustering in real time, where green points correspond to reflector predictions and red points correspond to non-reflectors, that is, noise or background objects. When comparing our system output to the image on the right, we see a successful prediction of the driving path. Standard performance metrics such as a confusion matrix, accuracy, precision, recall, and F1 score are presented to describe the results from applying DBSCAN to 1008 radar returns. The system accuracy was computed to be 84.13%, and the F1 score was computed to be 83.71%. The results were calculated by comparing the DBSCAN outputs to the ground truth reflector positions from the Vicon system. In conclusion, we believe that the detection of physical infrastructure with radar could be the key to autonomous vehicle localization challenges under extreme weather conditions. We explain the potential for intelligent infrastructure systems in transportation through the use of reflective localization landmarks. This work contributes to the development of radar processing techniques and also study the effectiveness of unsupervised learning for segmenting radar data.
We would like to acknowledge the support of the Natural Sciences and Engineering Research Council of Canada under the CREATE project on building trust in connected and autonomous vehicles. And thank you guys so much for tuning in.